Your laptop runs on clean digital logic. Every piece of data is a precise 1 or 0, and stray electrical noise gets rounded away. A quantum computer doesn't operate with that kind of safety net. It is an analog machine. Because it processes continuous analog states, the quantum information it stores is incredibly fragile. A microscopic fluctuation in temperature, a rogue cosmic ray, or a tiny defect in the surrounding materials can instantly scramble the calculation. To keep these delicate qubits stable, engineers bombard them with thousands of precisely tuned microwave pulses. But over time, the physical equipment generating those signals slowly drifts out of alignment, creating chaotic environmental noise inside the system. That physical fragility, combined with the drift of the analog controls, acts as a hard ceiling. It stops researchers from running the long, continuous calculations required to solve useful problems. Think of a quantum processor like an orchestra playing a highly complex symphony. As the performance goes on, the string instruments and horns slowly drift out of tune with each other. Up until now, the only way to fix that drift was to stop the music entirely. Engineers had to halt the quantum computation mid-calculation, spend hours running dedicated experiments to manually retune every single instrument, and then start the whole process over. For years, the consensus was that this recalibration bottleneck required better physical components. The industry assumed we needed decades of slow, painstaking improvements in pure material science and fabrication to make the hardware naturally drift less. The entire timeline for practical quantum computing was built around that assumption. Reaching true, uninterrupted fault tolerance was priced in as a hardware limitation, stretching years into the future. Then, a team at Google Quantum AI published a paper in Nature about their Willow processor. They stopped waiting for perfect hardware and applied an artificial intelligence software fix instead. Their approach taps into quantum error correction, or QEC. To protect fragile qubits, QEC weaves them together and runs continuous parity checks. These checks natively generate binary detection events that identify exactly when and where a math error occurs in the circuit. Historically, error data routed straight to a decoder program, which infers what went wrong and corrects the logical state. Now, Google gives this data a second job. They route a duplicate stream directly to a reinforcement learning agent, treating errors as a live training signal. The agent continuously monitors live error data. It intentionally nudges thousands of control parameters at once, learning which adjustments improve the system's stability. Physically retunes the microwave pulses on the fly without ever pausing the calculation. By unifying calibration directly with computation, the machine uses its own mistakes to constantly adjust its analog controls. It tunes the instruments while the music keeps playing. The researchers first tested this on a processor that had already been exhaustively calibrated by human experts and physical models. When they turned the agent loose on top of that baseline, it found an additional 20% reduction in the logical error rank. This grid tracks error rates. The team injected artificial drift to sabotage the machine. Spiking red lines show a traditional fixed policy degrading rapidly, but the blue line, representing AI steering, successfully tracks this chaotic drift, pulling errors down and improving stability 3.5-fold. The most important part of this experiment is how it scales. As you add more qubits and the quantum chip gets larger, the processing time required to train the AI agent does not exponentially increase. This factor graph shows why it scales efficiently. Because error detectors only care about gates in their immediate physical area, the agent doesn't solve the processor as one massive puzzle. It treats the system as thousands of tiny, localized problems running in parallel. These metrics prove the reinforcement learning agent is neutralizing the recalibration bottleneck and doing it in a way that will naturally adapt to commercial-sized processors. Maintaining a stable quantum memory is a challenge extending beyond the physical fabrication of the chip. This research proves that achieving fault tolerance is primarily a controls problem. While developing a new physical material takes years of iteration in a lab, a software-based learning loop can be updated and refined in a single afternoon. While the tech world has been focused heavily on large language models, artificial intelligence has been quietly accelerating the timeline for quantum viability in the background. We are approaching a tight technological feedback loop. Software is actively fixing the physical limitations of quantum hardware, which will soon allow that same quantum hardware to run the next generation of artificial intelligence. The machine is now using its own errors to correct itself in real time, outpacing the calibration speeds of human engineers and altering the developmental roadmap for modern physics.